What's going on, you guys? Welcome back to my channel. Today's video will be on two-way slabs. We will discuss design of RCC slabs according to the IS code provisions. So first, let's see what is a two-way slab. A two-way slab is a slab in which the aspect ratio of the slab is less than 2, and it can be simply supported at the ends or it can be restrained at the corners. So basically in this problem I will be showing you how to design a slab which is simply supported over the ends. So let's see what is the problem given to us. Design a RCC slab for a room 6.3 meter by 4.5 meter. The slab is to be casted monolithically over the beams, that is on the beam, and the slab is to be casted together with all the sides simply supported. It has to carry a characteristic load of 10 kN per meter square. So basically this is the live load in addition to its own weight, and use M25 concrete and Fe415 steel. So first step is always to calculate the aspect ratio. So in this case our aspect ratio will be 6.3 over 4.5, which will be 1.4. so clearly it is less than 2, so this is a case of two-way slab. So before we start, so the first step would be always would be to calculate the effective depth of the slab, and the depth of the slab can be calculated by using the span by depth ratio. So it is given in clause number 23.2.1. it's on page number 37. First step is depth of slab using span by depth ratio. So D is equal to span upon basic value multiplied by modification factor. The modification factor is taken anywhere between 1.2 to 1.5, and the basic value for different types of slab or beam is given in clause number 23.2.1, page number 37. So the basic value for simply supported slab is 20. So the span given to us is 4500 upon 20 and multiplied by let's assume 1.5, so we get it as 150 mm. Always take the shorter span for all your calculations, remember this. So let's take somewhere greater than 150, say 175 mm. Okay, assume the total effective cover as 25 mm. We will adjust the size of the bar later. So let's assume effective cover as 25 mm. So if we add the effective depth and the effective cover, we will get total depth, that is 175 plus 25, which is equal to 200 mm. Now the second step is to calculate the effective span of the slab. It is based on the provision given in clause number 22.1a on page number 34 of the IS code, and there are basically two conditions. The first condition is the span of the shorter span of the slab plus the effective depth, and the second condition is the span of the shorter span of the slab and the half of the support from both the sides, distance of the support from both the sides. So the support size is not given to us, so we will ignore this part. We will only see this. So Lx is 4500 plus the effective depth is 175 mm, so which is 4675 mm. If the size of the supports is also given to you, so you also have to add that in this, and you have to choose the smaller of these two values. So L effective is 4.675 meter. Okay, now the third step would be to calculate the total loads acting on the slab. So the third step would be load calculation. There are two types of load, dead load and the live load. So the dead load is the weight of the slab, that is density of the concrete in kilonewton per meter cube multiplied by the depth of the slab, which is 0.2 meter. We get 5 kilonewton per meter square. Live load given to us was 10 kilonewton per meter square. So if we add all these, we get total as 15 kilonewton per meter square. And we always calculate load acting per meter width of the slab for designing slabs. So I'll divide it by 1 meter, which is 15 kilonewton per meter, and we will also multiply it by 1.5 to get the factored load. So multiply it by 1.5, which is 22.5 kilonewton per meter. So you have the depth of the slab, you have the span, and you have the total load acting on the slab. So you can also now calculate the moment. Now the fourth step is calculation of moments. For that you can also refer table 27 on page number 91, and on page number 90 in clause D2, this is a special clause for simply supported slab. It says that when simply supported slabs do not have adequate provision to resist torsion at corners and to prevent the corners from lifting, the maximum moments per unit width are given by the following. I'll show you that. So this is what is given in the IS code. The value of mx, I'll zoom on that. Mx is alpha x WLX square, and my is alpha y WLX square only. So in both the cases you have to use Lx. Now based upon the aspect ratio of the slab, the various values of alpha x and alpha y are given to you. Now for our case, the aspect ratio was 1.4. so for 1.4 the alpha x is 0.099 and alpha y is 0.051. so I will write that down here. Alpha x is 0.099 and alpha y is 0.051. Now as per the code, the moment given to us was formula for moment was mx is equal to alpha x WLX square and my was alpha y WLX square. Note that I have used Lx on both the sides. So alpha x is 0.099 multiplied by 22.5 multiplied by 4.675 square, which is 48.68 kilonewton meter, and 0.051 multiplied by 22.5 and 4.675 square, which is 25.07 kilonewton meter. So you have moment on acting on x direction and moment acting on y direction. This is for the longer span and this is for the shorter span. So naturally you will use the maximum bending moment, because we always design any member, any flexural member, any tension member for maximum moment. So our design moment would be 48.68 kilonewton meter. Once you get the moment, you have to check for depth. So the fifth step is check for depth using the moment which you got in the previous step. So md is equal to 0.36 fck xu max b d minus 0.42 xu max 48.68. I'll write all of this down. 25 is the grade of the concrete, 0.48 d for Fe415 steel into 1000 d minus 0.42 into 0.48 d. So everything is in here, only the value of d is unknown. So if you solve for d on the calculator, you'll get d is as 118 mm, which is clearly less than 175 mm. So this is okay. So once you have given the check for effective depth, the next step is to calculate the area of steel in x direction and in y direction, because in 2S slabs the main steel is provided in both the directions. So the sixth step is calculation of steel. First I will calculate in x direction. The formula is 0.5 ck upon Fy 1 minus 1.46 m fck bd square b into d. So I'll plug in all the values here. moment in x direction, which is 46.68 into 10 raised to 6 upon FCK is 25 into 1000 into effective depth in x direction is 175 mm square into 1000 into 175. So if you solve this, you'll get something like 800 mm square. Once you get this, you can provide the spacing. Spacing is area of 1 bar upon AST required multiplied by 1000. So let's assume 12 mm diameter bars. So area of 1 bar will be 5 by 4 into 12 square upon AST required is 800 into 1000. So which is 141 mm. So let's take it as 140 mm. Now you can also provide the check for maximum spacing, which is 3D or 300 mm. So basically you can see it is less than that. Therefore provide 12 tor at 140 mm center to center. Now once you provide the steel in x direction, the next step is to provide steel in y direction. Calculation of steel on longer span. Again the formula would be same. ASTY is equal to 0.5 FCK upon FY 1 minus under root of 1 minus 4.6 m FCK BD square B into D. I'll plug in all the values again here. 0.5 into 25 upon 415 1 minus 4.6 1 minus under root of 1 minus 4.6 multiplied by the moment in y direction was 25.07 into 10 raised to 6 upon FCK is 25 into 1000 into the effective depth in y direction. So see here, this is the bottom of the slab, this is a bar in x direction, and above that the bar in y direction. Let's assume this. Okay, now the total depth was 200 mm and the effective cover was 25. So the effective depth would be up to this part. Okay, from the top up to this part. If this is the top of the slab, up to this part it will be effective depth for steel in y direction. So what we have to deduct from 200 minus 25, which is the effective cover, minus 6, because we are using 12 mm bar here, so minus 6 and again minus 6, so we get it as 163 mm. Okay, so put it here, 163 square into 1000 into 163, which is 446 mm square. Now the spacing in y direction will be area of 1 bar, which is pi by 4 into 12 square upon the area of steel required is 446 multiplied by 1000, which is 253 mm, which is equal to 250 mm we will assume. So provide 12 tor at 250 mm center to center. So what we got area of steel in x direction, we got area of steel in y direction. Now once you do this, we also have to provide torsion reinforcement in simply supported slabs, because the simply supported slab has a tendency to rise up from the corners. Suppose these are the supports, the slab has the tendency to rise up from the supports like this. It can rise up. so we have to provide torsion reinforcement at the corners. So what is a torsion reinforcement? It is basically a mesh like this. It is formed in the shape of a square and it is provided in 2 layers. Suppose this is the section I'm drawing, this was the plan. If these are the bars, so the first layer is provided below the main steel and the second layer is provided above the main steel. So it is given on page number 90. So I'll write down the provision of torsion reinforcement. Okay, so it is given on page number 90 in clause D 1.8. so if you want to refer anything about two-way slabs, you can also refer page number 90 of the IS code. It has all the details mentioned about two-way slabs, so you can check out at least once about that. It says that the area of tension reinforcement to be provided will be equal to 3/4 times ASTX. AST for torsion, which will be equal to 3/4 times of ASTX. So our ASTX was 800 mm. So 3/4 into 800, so that is 605 mm square. And also it says that, I'll show you that clause if you want to. Here it is mentioned in the clause, torsion reinforcement shall be provided at any corner where the slab is simply supported, because it may rise up, and the area of reinforcement in each of the layers should be 3/4 of the area required for maximum midspan moment, which was ASTX, and it should extend up to a minimum distance of 1/5 of the shorter span. So the length of the reinforcement mesh would be, which will be 1/5 of the shorter span. So size of mesh will be equal to Lx upon 5, which is 4675 upon 5, which is equal to 935 mm. Provide any diameter bar. I'm using 10 mm dia bars. So spacing would be pi by 4 into 10 square, which is area of 1 bar, upon 600 mm, multiplied by 1000, which will be 129.93 mm. So we will round it off to 130 mm. So that's all with the design of two-way slabs I have provided. So design summary would be, now forget about the summary, I'll show you the final diagram what it will look like, so you'll get the idea. So this is what the diagram of the slab should look like. This is the shorter span. This is the main steel provided in the shorter span, which was 12 tor at, what was the spacing for that? 140 mm center to center. And again this one is the longer span. And it is just about the shorter span steel, as you can see, and which was 12 tor at 250 center to center. And finally this is the plan area. As you can see, this is the mid span steel, and at the corners I have provided 4 meshes, which is for torsion steel, and this is the distribution steel, for which you have to provide minimum area of steel. Furthermore, you can also provide checks for all the design which you have done earlier, Namely, there are three checks: the shear check, deflection check, and the development length check. For that, I have made a separate video for one-way slabs, so the checks would be same for two-way slabs also. So I'll give a link in the description to that video, so make sure you watch that video also, so you can also see how the checks are provided for slabs. And I hope you understood the design of two-way slabs, and if you have any doubts or queries, please comment down in the comment section. I'll make sure to answer all of them, and if you want me to make more videos, please suggest me. And I hope you like this. Please like, share and subscribe. Till then,